only people are not from Seattle carry umbrellas. The first approximation. Right here?
Right. Okay.
Okay, what I'm gonna give a talk about the nuclear fragmentation region and high energy nucleus and hadron nucleus collision. This is work which just appeared on the web with Soren Schuften and Streamway Sound for the first part of it. The second part of the talk is going to be about work which is in progress with and Bruce to pipeline. And the issue is the following, is that the fragmentation region is a region where baryons sit and valence quantum numbers sit after a collision. So you might think that if you wanted to make a high density of baryons, this would be the region you would study. Now, the problem theoretically is it's probably hard from first principles to do calculations at low energies. Maybe it's possible, maybe some people might even think it's possible. Now, it's certainly possible to do the calculations, but at some point you have to justify all the assumptions which go into the computations, and that's kind of hard. On the other hand, we do have a theory of what happens at very, very high energies, and we might think that we could be able to understand the fragmentation region and what happens in that kinematic region when we have a very, very high energy scattering. And the reason why that might be interesting is that because the valence quantum numbers are there, you might, sounds a little counterintuitive at first, but you might be able to make a matter distribution which has a high baryon density in it. And by high baryon density, I mean rate basically number of baryons to number of mesons is some number which is of order 1. Okay. And, you know, if you make a system which has number of baryons over number of mesons of order 1, number of baryons over number of mesons is sort of like the baryon to entropy ratio. And that might be conserved in a collision. You might even think that if you have a subsystem which is thermalized, when you went to very early times, if you had a high NB over N entropy, that would be the value more or less which you get at late times. Now that will be subject to all sorts of caveats because the matter which you produce in the fragmentation region, I will argue to you, will have much more difficult time thermalizing than the matter which is produced in the central region. But we've got a long way to go to get there. Okay, and one of the questions we have to ask too is when can we begin to use a high energy description for nucleus-nucleus collision? That's a bit of a mystery also, because if you think about a very thick nucleus, a nucleus say as thick as the moon, okay, and you run a projectile through it at any reasonable finite energy, it's not going to go all the way through the moon. But at least for some part of the trajectory through the moon, you think you should be able to use some methods of high energy physics to describe the particles which are produced in the baryon density, which is there. Maybe at the end, where the projectile gets stuck in the moon and it's moving very slowly, you might not be able to understand it. But you should be able to understand it in its first steps. Okay, that might be one direction you can take this. Another direction you might be able to take it is maybe if you understand what happens to the high energy limit, it'll give you some idea to handle the low energy, maybe. But the first problem I want to deal with is when basically a projectile nucleus flies through a target nucleus. Alternatively, one can think about a proton going through a nucleus. So we'll see those problems are not so far away from one another. So one is, yeah.
I'll just ask a practical question. So how do you want to measure anything in the fragmentation region of the high energy?
I don't measure anything.
I know that, but nevertheless, I mean, right, to make anything useful out of it, so basically you have to put something at 0 degrees around the
easiest way to measure things in the fragmentation region is to run a target and measure things around the target. Don't do a center, right, don't do a collider.
Fixed targets.
But then if you really want to go to really high energies, then you have all these problems. And then people have some clever ideas for getting some information. I should say one area where this has some practical importance is in cosmic rays, because in cosmic ray shower development, you're measuring what happens in the far fragmentation region. And what's critical there is what happens to the fragments in the early collisions there. And I'm going to argue to you that, in fact, the fragments are pretty far distorted from what you would expect from. People always assume scaling. Okay, PT distributions don't grow, X distributions are the same. I can argue that, at least as far as PT is concerned, there's a big difference, and in fact, there's a significant rapidity shift of particles which occurs. It sort of has to, if you have a large amount of PT, as you might expect when you go to very, very high energy scattering off in the nucleus, then the rapidity has to shift down just so energy is conserved. So the whole initial structure of the collision probably looks, at some limit where you're very, very high energies, a proton scattering off of the nucleus looks more like a nucleus scattering off the nucleus at lower energies, because basically all the fragments are shifted down in rapidity. And one of the problems they have in cosmic ray experiments is when they look at the highest energy cosmic ray, they say that above some energy there's a shift in the abundance, and it's got more nuclei in it than it has protons. So one question I have is that really real, or is that something associated with the change of particle distributions in the fragmentation region? And I don't know. This is a lot further from where I'm playing in kindergarten, and you want me to play in first grade. First grade's too hard for me. Okay, I just want to set up the problem and do some simple things. And also, you know what I'm doing? So I'm looking for some low-hanging fruit, some problems which will have some lasting social value because they're cute to say, which you can solve, and then I probably will move on. I'm not somebody who develops things like that. So that's part of the story. Okay, so when can we begin to use a high energy description for nucleus collisions? That's when there's a central region, a particle's not formed within the nucleus. That's when the gamma factor of a particle times its formation time is much larger than the nucleus. You have to have some particles in the central region. And that puts a requirement that E over the typical transverse mass curve of a particle has to be much larger than R. 1 over MT is the sort of rest frame size or time, and E over MT is this gamma factor. And that means the width of fragmentation regions and rapidity over the order of log of an 8 to 1/3. And that leads to energies which are greater than 30 GeV. And this is the conventional region where you begin to think about its high energy. You begin to throw around words like color glass condensate or small x or whatever, even though probably it's not even, strictly speaking, valid there until you get higher energies. You do what you can do. This is the flipper?
No.
Oh, that's that.
You turn the projector off also on this.
Oh, well, I can do that. This is the right one?
Sure. Let me see the. Okay.
It doesn't work.
It doesn't work because it's not connected.
See,
Now I can give you a call.
you're now exposing my incredible ignorance of modern technology. Okay, there we go. Okay. There's another region where the high energy limit works also, and that's where the gamma, the projectile, is much, much larger than 8 to 1/3 of the target. And that's where many of the fragments appear outside the nucleus. The projectile kind of goes through the nucleus. And you would think you could be able to describe what happens to particles here, even though you probably don't have a fully developed central region. Of course, on the far edge of the nucleus, there'll be overlap of fragments from both nuclei, and that'll be complicated. But you sort of believe that you should be able to use a high energy description, at least for part of the nucleus as a projectile sweeps through it. Ultimately, the considerations I'm going to use might have some application there, but I'm going to consider a simpler case. I'm going to consider the case where this thing just goes all the way through the nucleus. I have a situation where I have a fully developed fragmentation central region, but I actually look in the region where the baryons sit, where there are some finite density baryons. I look at rapidity regions near the target rapidity or near the projectile rapidity, a few units around that. And I'm just going to try to describe what happens in that region. What I'm going to do is I'm going to develop a classical theory of classical fields and baryon density. And this is going to be similar in spirit to the work of Shenka and Shan. I will consider the fragmentation region when there is such a fully developed central region. And in principle, this might be generalized, but I'm not going to. Okay? Maybe later. One of the things you notice in this situation immediately is that there's a huge asymmetry. In this region, if you think about the saturation momentum of the target, we'll think of this as the target, the things addressed here. It hasn't had a chance to evolve very much. So the saturation momentum of the target is something which is, sort of its scale at low energies. And that'll have an 8 to the 1/3 in it, but won't have any evolution in rapidity. On the other hand, this object, when you go to this rapidity, as it had a chance to evolve, so the distribution of partons inside the projectile is as measured at the rapidity of the target, has lots and lots of gluons in it and C quarks, which have had a chance to be produced in the evolution from the rapidity of the projectile down to the rapidity of the target. That is, the projectile saturation momentum is much larger than the target saturation momentum. We can see that explicitly when you look at these expressions. The saturation momentum of the target has this factor e to the kappa delta y. Delta y is a few, so it's not very big. But the saturation momentum of the projectile has this huge rapidity enhancement, and if you use kappa of about 0.2 to 0.3, you can easily get to quite large saturation momentum of the projectile.
Yeah, so it sounds like you're describing the hybrid picture that people have been talking about much of last week, where you have large X partons from one proton or nucleus colliding in a small X cloud of
Yeah, that's right.
Okay. Is that the answer?
Well, yeah, but you have to calculate something.
I'm just saying lots of people do a lot of...
Yuri, I think it's the same physical situation, but with different Lorentz rate. So usually in this hybrid one, things of kind of high energy dilute things hitting a dense target. Here it's a dense target hitting a high energy hitting a dilute thing.
Well, but the cross sections of boosted variance.
Yeah, you see lots of times when you do the high energy scattering, you don't bother about understanding the recoil of particles in the collision. And that's going to be essential in the target fragmentation region to calculate the density. Because what we'll see in a minute, that the baryon density gets a huge enhancement due to the sequential nature of collisions there. That to get that enhancement, you have to actually build in the recoil effects of the target particles when they scatter. And what I want to do is I don't want to just develop a momentum space picture of the distribution of particles which are produced. I want to develop the space-time and momentum space description so that I understand where the energy is being deposited as I go through the nucleus, so that I eventually, at some reasonably late times in collision, when I can treat trajectories as more or less classical, I can match onto some hydrodynamic description. Of course, early on, you have to treat the problem quantum mechanically because delta P and delta X are not much larger than 1. But once you do that properly, then you can do the evolution early on with some sort of quantum mechanical treatment. But then later, when it's settled out, so delta P spatial gradients are relatively small compared to typical momentum in the problem, then you can match that on to some description like a transport or hydrodynamic calculation, like what you always do, like what Bjorn's been doing with his pioneering work on the central region. And I'd like to be able to develop such description in the fragmentation fragmentation region. Now you can see what the problem is. You have a picture, if you have a large nucleus, and it gets scattered, maybe in the initial distribution it gets compressed. You sort of expect that that compression is going to be homogeneous as you go across the nucleus, right? Thing gets here, makes a density, here it makes a density. Maybe in time it's not. Maybe there'll be some gradients because of time dependence of it. But in general, the typical initial compressions as you go are going to be pretty uniform. It's not true for the gluon radiation, because the gluon radiation, when you strike the first one, it makes a gluon. You strike the second one, it makes a gluon. Third one, it makes a gluon. So the distribution of gluons as you go across the nucleus is going to be a racking distribution. So you're going to have kind of a difference between the way the gluons are treated and the way the quarks are treated. One has to solve that and understand how to deal with it. And it's a problem in strong fields because the nucleus has strong fields. And you see immediately, however, the common ground is what you're going to do is because of this asymmetry between the saturation momentum of the target and the projectile. The target can be treated as a small source role, and the projectile has to be treated as a large source role. Okay? And because of, I'll argue that in a minute why that's true. There's limits to that description also, but largely it's true. And so that lets you do some approximations on it, which makes even a high energy nucleus fission look sort of like a high energy proton nucleus collision. At least where most of the energy and logarithmically most of the particles are produced. That's the case. We'll see that on the next one. Okay? Everybody's okay? Okay, so the point of the story is that LHC energies, this might be on the order maybe even 5 or 10 GeV in the fragmentation region of the target. That's a big scale. And one might even believe that one can do something there. Okay, and one of the things which is true is when you're at momentum scales, which are less than the momentum scale of the saturation momentum of the projectile, that's a region where the color fields of this nucleus are large. Okay, once you get less than this scale, and they reach their maximum when you get to a momentum scale. Well, the maximum you can see things. So there'll be another effect which will come in and cut off the effects of the color fields when you get to saturation momentum of the target. In general, you have big fields from the projectile whenever your momentum less than this scale, but their effects will get somewhat dampened by screening effects once you get down to that scale. And you can sort of understand what happens if you were to calculate the distribution of particles by scattering to an asymmetric projectile where you have a saturation momentum of the target, which is much less than saturation momentum of the projectile. You've probably all done this, so I won't beat you over the head with it, as I might have to do in other audiences. But the point is that very, very high PT, where your PT is large compared to both that of the target and the projectile, generically this goes like 1 over PT to the 4th. But when you scale this by the area, it has to be dimensionless. So you have to have factors of Q saturation squared of the target, Q saturation squared of the projectile. Okay, and this is the region where PT is larger than both scales. Then there's a region where it's between one and the other, and that's a region where basically the distribution is just the distribution inside the target, which is in leading order just a Bremsstrahlung distribution that goes like Q squared saturation on target over PT squared. And then there's a region where the fields of both the target and projectile are both large and have a big effect. And that's a region where this even gets cut off to something in the order of a constant. So if you use this, you can then calculate dn dy by integrating over PT. And you see the dominant region is in here. And you pick up a logarithm of the lower momentum divided by the upper momentum, which is some slowly varying thing, okay? And this region doesn't contribute very much. This region contributes something of order 1 and is beaten by a logarithm. So in some sense, it's not such a big effect for particle multiplicities in this region. But in fact, logarithmically, this intermediate region is the region which dominates. There's also, it's different if you calculate, well, actually, PT squared, you'll run into this. What I should really be doing here is PT, and this would be here the projectile. If you put in PT squared here, you're running logarithmic infinities. So you really want to calculate an average PT, which has a power less than the square. And if you do that, you'll find that the typical PT scale is the order of that of the projectile. And that's a very bizarre situation if you think about it, because the multiplicity isn't increasing very much, but the average PT is. And that has the consequence that the transverse energy, if we were just to measure the transverse energy, that would be something which would be growing at wooden scale. Okay, and you know, one knows that distributions of particles, at least at Rick energies, don't change very much as you go to higher and higher energies. This would be the fragmentation region here. This is an energy, center of mass energy, which is going up. You calculate the square or something for the lab energy. But in any case, in this region, you see approximately scales. So this feature that the number distribution doesn't change very much as you go to higher and higher energies seems to be more or less true just in the cursory glance of the data. On the other hand, you also don't see much increase in the average PT of particles in this region. And that's a little bit of a surprise. You do begin to see changes in average PTs of particles when you go up to LHC energies when you're in the central region. I really don't know what happens in the fragmentation region. I don't really know what degree has been studied even in the fragmentation region at Rick energies, because it's hard to do measurements there. But you know, these kinds of scaling arguments should be true if you go to high enough energy. Okay, so in addition to putting a tremendous amount of transverse energy into this region, there's another effect which occurs in the fragmentation region. Imagine you take a high energy sheet of colored glass and it runs through the sequential row of nucleons. Okay, it hits the first nucleon first. It gets a velocity v. So by the time it hits the second nucleon, this separation is 1 minus v. So you might have thought there'd be a compression factor which goes like 1 over 1 minus v. That's not quite correct, because when you calculate a compression factor, you want to calculate it in the co-moving frame of these struck nucleons. And there's a gamma factor you have to kill due to Lorentz contraction. And when you build that all in, the kind of increase in co-moving baryon density you get will go like gamma, not like gamma squared. 1 over 1 minus v would be gamma squared. Okay, so you can now use this to estimate the kinds of energy densities you might get in these collisions. Remember that okay, so there's a typical Lorentz, that the Lorentz gamma factor is gonna go like typically the projectile saturation moment R, because of these kind of elementary considerations. So the initial baryon density is going to be of the order of Q squared target times Q projectile. Okay, that's maybe not so exciting, but because Q projectile is quite big, your initial baryon density can be quite large. The surprise is when you calculate the multiplicity produced particles per unit area. That goes like q squared target, okay? And so if you then put in the initial longitudinal scale on which these particles are produced, which is 1 over a q projectile, again, you get a density which is going to go like q squared target, because that's just the density per unit area to begin with, times the decrease in time scale associated with the saturation momentum of the projectile being big. So you get parametrically the same dependence. And that's interesting because that says that if you calculate NB over the multiplicity as you go to higher and higher energies, that's something which is going to scale. It's going to be a number. It doesn't depend on the energy.
So this is only true in the fragmentation region?
Yeah. Yeah.
And then that assumption goes in because you're using only Q projectile here.
Yes, I would use.
So if you were not in the fragmentation region, you wouldn't have this scaling of going with Q projectile, right? So that's
Yeah. I mean, several issues would be there. Is the net Baryon density outside the fragmentation small in rapidity. It only has sort of kind of a maximum finite number inside the fragmentation region. So that would be the biggest effect, which would dilute this, is that if you vary the rapidity, the initial density variance in that rapidity is very good.
but this would enter here by basically not having the scale with Q projectile. This is only true because this is the larger one, right? In this case. So
Yeah, that's right.
Okay.
But that, you're gonna, it'll be, if you move out in rapidity, this won't be Q projectile at the rapidity of the target. It'll be Q projectile at some other rapidity, and so that number will, that'll also reduce the effect too. So this is kind of nice because if you have some kind of expansion where, say, the number of gluons is roughly conserved, that means the NB over N gluon you start with will be the NB over the N gluons you end up with. And that's sort of like, but probably the number of gluons isn't conserved. And the reason why that's true is you can see from this argument immediately. The region where most of the gluons are produced, and most of the energy is coming from, is the region where the fields aren't the field strength associated with the nucleus is not completely how can I say it? It's a region where when you're calculating this density of gluons, okay, the density of gluons in this region starts off at the saturation momentum of the target and ends up at the saturation momentum of the projectile. When it's at the saturation momentum of the target, the gluons which come from the nucleus, which are the ones which are getting produced, are very strong. But by the time you get out to the transverse momentum of the projectile, the bigger scale, the gluons which come from the target, the field is not so big. So the region where you're producing these gluons is actually an interesting region. It's not a region where there's a full nonlinearity of the fields from the target. It's a region where, in fact, the target fields are becoming weak. Okay? So it's not going to be a region where you expect, at least very early on in the collisions, the interactions are going to be very strong. It's also a region, by the way, because of this fact that when you calculate the gluon field associated with the target, which gives rise to these gluons, that's a region where you can calculate the first order in the field strength of the target. So it will be, this is a problem basically where you're to calculate the number of gluons in the average PT, the problems are very, and you know this from what you did along with one PA, that in that region, that's the region where you can basically treat all the nonlinearities of the projectile, but you have to treat the nonlinearities of the target perturbatively, at least early on in the collisions. Now later on in the collisions, because you look at this thing for a long time, it's perhaps true that one may have to worry about interactions at later times, but that's probably at a time where the fields are moving enough so that you can have some sort of transport calculation. You were looking like I was saying something. Yeah. You're happy? You're more or less happy?
Just trying to wake up.
Okay. Sorry. I'll speak with a more monotone voice.
Don't keep me awake.
I'm good at that. No, okay. So what did we do with Shri and with Soren? What we did there is we tried to consider this problem to get an idea of both what happens in momentum space and space. What we did is we considered a simple problem. We considered a distribution of particles, which we'll call baryons. At first we did it with scalar fields, then we did it with quarks, and in the paper it's done with quarks, but you can understand the physics with scalar fields may be a little bit simpler. And I want to go for understanding here, not for precision. So what you do is you start with some distribution of particles, scalars say Bose condensative scalars, like things which all have very low momentum, so that they're basically particles which are at rest, okay? And then what happens, a sheet of colored glass comes along and scatters off these particles at rest, and they start moving on the other side. And that's a very simple problem to solve, because if you calculate the Klein-Gordon equation in the presence of this delta function potential, you'll find that basically the initial distribution, which are free particles, which we're going to take very long now, will get scattered, okay? And this eta of xt is basically the integral over x minus as you go across the sheet of the vector potential, something which you can calculate in terms of classical fields. And so that the scatter fields basically are just kind of trivial scattered fields. And you can use that to calculate the currents after the collision. Again, this is just a simple calculation of phi dagger grad mu phi, which you can all do. And you get these kind of simple expressions, okay? J plus is big because this is the component which gets really kicked, well, yeah, we'll see in a second. Actually, J plus is going to be small the way I've done it, because K plus is going to be something of order of rest mass particle, which is of order of a rest mass, because I'm looking for the initial distribution of rest. PT squared is of the order of the saturation momentum scale. So this is going to be a big component. And J tilde I, like in the three bears, is going to be just right at some intermediate scale.
Well, why is there a plus in the J tilde I on the right-hand side after PT plus KT?
Let's see.
Those are typos.
That's a typo. Yeah, that's a typo. Don't believe everything I write.
That's right.
Yeah, I know. It's hard to believe.
It's hard not to believe that.
So you can now calculate the induced gamma factor after the collision, and not too surprising, that's PT squared over 2K plus squared for the reasons which you stated before. So this goes like Q squared saturation squared over M squared, or the gamma factor goes like Q saturation over M, where M's the mass of the initial particles, which were in your distribution. Okay, and then you can use this to calculate the local baryon density, and the local baryon density, not too surprising, turns out to be Q saturation over M. So if you identify the gamma factor as Q saturation over M, you get precisely the result which you have in this McLerran analysis. And this is right after the collision. Now we did more. We actually calculated what happened as we let the fields evolve. We did it with Wigner distribution functions, and this is sort of shows typically what happens. These things scatter. You produce distribution of particles. You have to boost into a frame, which is co-moving with the typical longitudinal momentum distribution of the produced particles to get such nice symmetrical pictures. And you can also calculate the distribution in time and rapidity. These are plots as a function of rapidity for each curve, and then you vary the time as you're going in this direction. And it shows how things spread out, and it shows how the things varying as you go across the nucleus. You can do all of that. And that's sort of interesting, because then that should give you kind of initial conditions for the baryon distribution of some transport calculation. I don't want to go into the details of it, because anybody can do, I mean, it took us a while to do the calculation. Anybody but me can do this calculation. Okay. Yeah.
So, as you increase time, it looks like your baryon density is moving to the right, to higher rapidity. You expect to see more stopping, right? Is that something I'm missing?
Well, if you have a thing which gets hit by a sheet of colored glass, okay, it's going to start moving to the right. But remember, when you do momentum space rapidity, it's also correlated with coordinate. So a thing which is over here has a different rapidity than a thing which is over here. So you also see the effect of the projectile when it's sweeping through the target. So there are two effects. One is that the particle after collision gets the momentum space rapidity, but then there's also this sequential effect that is the projectile moves the target. It hits things one after the other. So it's a mixture of those. To really see what's going on, you really probably want to look at late times.
So long time ago, 15 years ago, you, Derek, Gaza, and myself wrote the paper on Baryons.
Yeah.
Is this consistent?
We haven't, no, that paper was about how the baryon, if I remember right, we saw the baryon diffused down to the central region, right? And we had to calculate these next to leading order.
Double evolution.
Yeah. And no, this.
We also had the classical results first.
I don't know. That's a long time ago. I can't even remember a week ago. Maybe your memory is better. Okay. It could be.
All right, so you haven't tried campaign.
No, I haven't tried that. I know we never worked out the space time.
No, we didn't look at the space time, but in terms of rapidity, not coordinate rapidity, but momentum.
Yeah, momentum space rapidity. Very specific. And in fact, all of the kinematic vectors and recoil factors are built into this lowest order calculation when you require that k squared is equal to 0, because basically, you get a transverse momentum kick. K plus is conserved, so that K minus has to change in order that K squared can be on shell. And that change in K minus is what gives you the longitudinal momentum kick. And that's usually what's ignored in the Eikenall approximation.
But
You just don't take.
We wouldn't have known the Baryons anywhere.
Well, in the Eikenall approximation, you ignore the shift in K minus, because you're just looking at the coordinate trajectory. And what I'm saying is, when you really look at the projectile fragmentation region, you're interested in the momentum of the projectile fragments after the collision, the longitudinal momentum. So you have to calculate that longitudinal momentum to understand how it gets kicked. It's trivial to do. It's just a consequence of
we did a lot of it.
problem.
We also had a follow-up paper with Javier that said that when we actually looked at production cross-section. The paper with you, we just looked at distribution and wave function.
It could be.
There are things to compare with.
Yeah, I agree. I'm not trying to say that we're the first time who computed the scattering of a particle when it goes through potential. But I think we are the first to try to seriously generate what that coordinate space distribution looks like, so one can do something with it later for some kind of calculation to calculate the evolutionary matter distribution. But in any case, all of this is kindergarten stuff. Okay, this is not what I'm presenting to you is not very sophisticated. I don't want to try to present it as if it is. Okay.
So here the baryon, incoming baryon number is only in the target? Or do both contribute? It's only in
It's
one of
only
them?
the target because basically I've treated the nucleus as a sheet of glass.
Right.
So all of those things went all the way down the beam pipe.
So when it comes in there, that's the blue line outside the line on the left, right?
Yeah.
And when it hits, it kind of starts stopping. That's when it becomes red. Or,
That's right. That's the
Hiding
stuff
out.
which has gone through the sheet.
and it somehow it moves to the right. Is that numerics or?
No, you have to shift things so that you take into account the net. To make a nice symmetric picture, you have to shift into the average frame where the average momentum of the produced particles is 0.
Mhm.
Right? Because it's going to be produced as a co-moving distribution, so that shift's been done, and the shift isn't perfect for everything. Right? But it more or less works.
You're saying the thing on the left is not sort of center of mass.
That's right. It's not the
Just
center of mass.
produced
It's neither the center of mass nor the target rest frame. It's a frame which is kind of moving with the baryons after they scatter. So that's sort of giving kind of an intuitive picture of it. If you did it in rapidity, space-time diagrams aren't in rapidity. If you did it in rapidity, be some overall shift. Okay. Okay. So the next question you have to ask is, once you've got the baryons there, you have to calculate the gluons. That's only part of the problem. You expect maybe a steady state rate of gluon production as the thing goes through the sheets, but the spatial distribution is going to be a bit weird. And I remember many, many years ago, back when people were first considering hydrodynamics, Keokayanagi and I worked very, very hard to try to develop some source terms for hydrodynamic equations to describe the fragmentation region, much like what Bjorn has been doing. And we went crazy. Now, Bjorn has had some insights into it, which are certainly much improved. But it is a problem which is very easy to get confused by, and I get confused by it constantly and interminably. And so the only way I could figure out to deal with this problem was to define a simple problem which you can solve, which is kind of a nice problem because nobody solved it before. Maybe it's not such a nice problem because it's important, but it's nice just because it's ungathered. So what I want to do is I want to consider a classical colored test particle at rest. So I just say I have some colored test particle which is sitting here. A sheet of colored glass hits it, it has some color vector, and after the collision, this particle gets scattered. And we know how to do that scattering already because classically, I solved the problem quantum mechanically. It's surely the classical problem, it's simpler to solve. And indeed, it is just a very simple problem. This is a problem which you can do it. And that I can do in about a week. Okay. And it's just a question of F equals ma as this classical electromagnetic field gets accelerated. And that's going to do nothing but reproduce what we had before in the classical limit. The interesting part of this problem is that this thing has some Coulomb field, which is associated with it. And two things happen after the sheet passes through these Coulomb fields. Where it's intersecting the sheet, these fields get accelerated. So there'll be radiation which is coming from these Coulomb fields. In addition, there'll be the radiation of this accelerated particle. In electrodynamics, you only have the acceleration of the particle because the fields are neutral, they don't get accelerated. Here you have this extra contribution. And this classical contribution of these fields hitting the sheet and getting twiddled by the sheet passing through it are what produce the uniform distribution of rapidity of gluons in the central region. But you should also be able to calculate in the region of rapidity, which is close to the rapidity of this. You should be able to calculate that Coulomb field anywhere. Okay, and so it's a nice little classical problem. what you have to do is you have your classical test particle. This is a source which is weak in strength. This is a field to all orders. It passes through this thing. This thing gets classically accelerated. So you know the trajectory of this particle. This is all in linear order, by the way, where this field is small. And then you can also calculate the gluon field which is produced by this. Now, it's not such a hard problem for the gluon field either, because I've argued to you most of the gluons are produced in a region where the field which comes from the source is weak and can be treated in linear approximation. So the problem you have to solve is a linearized problem for the fields which are produced by this thing, all orders in the strength of this, the field associated with this object when it passes through. Here you're looking like confused.
Yeah, it seems like what you're talking about is Bremsstrahlung.
It's Bremsstrahlung, but ordinary Bremsstrahlung comes from the acceleration of this particle. There's an extra contribution which comes from the radiation from the gluon fields.
So it's not going to be
Right.
important.
You know, when you do ordinary scattering, right? Okay. What you do is it's this graph which contributes, right?
Right.
But there are also diagrams which come from this and come from this.
So for a moment, it seems
And if you're in the central region, these don't give a contribution. So basically, you can work in a gauge, radio gauge, where these terms don't give any contribution in the central region. It turns out in the fragmentation region, there is a contribution from these terms, which are radiation from the source, and there's also contribution from radiation from the field. And to do that, you have to work to all orders in the strength of this field to get the all result that it can be done.
Larry, I think there's a simple way to get the answer. You decide what radiation you're looking for, and then rapidity, and then you boost to a frame where the radiation you're looking for has only transverse momentum. And so what happens is now you boosted your particle too, so it's a particle scattering on your shock wave. And then I believe the answer to the radiation is you calculate the gluon distribution of your particle, most order, simple logarithmic calculation, up to the saturation momentum of your sheet, and that should be the answer.
That'll be the answer for the momentum space distribution of the response.
It'd be the number of momentum space. Yeah.
However, we want to also calculate the coordinate space.
There's an advantage to doing the other way, right? I tried to do this both ways, and it's in a Polish proceedings for someone. And to some extent, I could calculate both ways, but not completely in the way that you're trying to do it. But you get the answer, of course, in the other frame. See, if you're looking for it's a question of whether the gluons are right movers or left movers. Suppose your shock wave is left moving, and you have your particle right moving. Go to a frame where the radiation is slightly right moving. It means it comes from the particle. Then you just calculate the number of gluons in the particle before the collision up to the saturation moment of the shock wave, and they're all free, obviously, because you're hitting this gigantic thing, and that's the number of density particles. Doing it the other way is a very complicated thing, because thinking of it more quantum mechanically, the shock wave is a distribution of quantum gluons. A certain number of them are freed by the particle, but that's a very hard calculation to do, because it's a small fraction of them are freed by the particle.
It sounds like Larry is more like the former.
No, he's more like the latter one, because he's trying to calculate what happens to the classical field of the shock wave and how much of it is produced. And that's like in the quantum language, the shock wave is built of quantum gluons. It hits a small target, tiny target, and then you want to know how many of that many gluons are free. And that's a very, very, very tough problem.
All that may be right. I mean, the place where the problem for us becomes a little bit complicated. First off, we need to know the distribution in transverse coordinate and longitudinal coordinate. So we have to build in all the recoil effects, and we want it for each external field. So that's a complication. The other complication we have is that we have to properly get the interference between the emission from the accelerated particle and the radiation, which is coming from the stellar fields, because there are two contributions, and they add in amplitudes. But it may be, I have to look at your paper. Honestly, I didn't know about the paper, so maybe.
This is the Biało's 80th birthday.
I should know that one.
So that's
You were in the audience.
Yeah, I was, but you probably calculate the momentum space distribution.
Oh, yes, absolutely.
Okay, and what we're interested in the field, and the field actually, in language of Wigner distribution functions, the field comes from the amplitude, and so they're probably complementary. At minimum, so you switch check. At a maximum, you've already done the problem, so you can.
No, I've done what you're trying to do.
Okay. But okay, so the idea, the way we solve this problem is actually kind of amusing. You have to work in the right kind of gauge. So you first consider your classical test particle at rest, and it gets accelerated. So you compute the velocity of the color test particle after the collision. Okay. But then to calculate the field associated with this
so you walk out.
So to calculate the field associated with the test particle, first you have to do some nice gauges. And one thing you want to do for your background nuclear field, I had to work in two-dimensional transverse gauge where x hat minus is less than 0. The reason why I did that is because if I work in that gauge, okay, basically there's no, the current associated with the source doesn't oscillate, right? Because initially the source is pure coulombic, okay, on the side of the sheet where this exists, and because of that, A0 is 0 in that gauge, which means that grad mu and J mu is just equal to d mu J mu, which is TDT rho, and so the source is constant. And then for the fluctuation field, in order to solve it, I had to use delta A minus is equal to 0 gauge. I worked in sort of a light cone gauge also for the source field. And the reason why I did that is, actually this should be J plus, is I didn't want, because there is a component of J plus for the source initially. I didn't want to have a contribution there. And that what I do by this is I make by using these gauges, I can make it so that two things happen. One is that the field associated with the source nucleus doesn't recess, it doesn't evolve in time. And the other thing that happens is that that when I look at my boundary conditions and I go across the sheet, I have no multiplication of set functions times delta function. And in fact, the transverse field is continuous across the sheet in this gauge. The longitudinal field, the small fluctuations longitudinal field jumps, but the transverse field is perfectly continuous. And what that means is that the radiation in the four light cones given entirely by the transverse field. In this background field, there's no field for x minus greater than 0, no background field. So it's just 3 equations. So to calculate the radiation, what I need to do, I calculate the Coulomb field at the source, I calculate what the field is at the sheet, and then on the other side of the sheet, I solve the 3 equations of motion for the field, and you can do that. And we're in the process of cleaning this up. We have an answer, but the answer is not fully stabilized yet. And we've also are calculating the technical issue, which makes this a little complicated, is the two contributions you have. When you have two contributions and you square them, you have to be much more careful about the signs than if you have one contribution and you square it. So, you know, there's signs and factors of 2 and square roots of 2, which ordinarily I wouldn't be so worried about, which I have to be worried about here to get right.
That's why you have collaborators.
Yeah, that's right. They're good collaborators. Yeah, but in any case, you know, we actually do have an answer for it. And then the question is, once you get the answer, first off, we'll write that up in a fixed background field. And then the next question is, what does this really mean for the initial conditions with the space-time distribution of the radiation? And how do these things look together? How do you really think about the problem in a proper way when you both have radiation and the valence particles?
Yeah. So for a diagram junket, I mean, are you saying the same like myself? Are you saying that you calculate in Ramstrahlen, but now you allow recoil?
That's right.
Is that the difference from the standard?
That's right. You're allowing recoil, and you're calculating amplitudes. You don't calculate amplitudes squared. You need to know amplitudes because amplitudes will give you the space-time distribution. Bigger distribution
Right,
functions,
you need the
amplitude
field.
lines,
So you need the field in that way. And recoil is in that foreground Ramstrahlen vertex or in both foreground vertices?
Well, what happens here, this thing recoils, so this momentum, you know, the longitudinal momentum of this shifts, okay?
Right, but which vertex is non-icon? There are 2 vertices here, right? There is let's say this vertex and that vertex. Are both of them non-iconal or just the right one?
Well, I don't think we don't treat this iconally here either, because what we're dealing with is we're doing things in the fragmentation region, so this particle is relatively small.
But using non-iconal
In fact, initially this is at rest.
but that would be energy suppressed.
What would be energy suppressed?
Using treating the left vertex subiconally is center of mass energy suppressed. Treating the other vertex subiconally.
Well, I think you maybe are talking about particles which are produced in the central region, but I'm talking about particles which are being produced here with relatively low longitude.
No, I understand you're looking at the forward region.
Yeah, but that longitudinal momentum here is of the order of this thing, and I don't think an iconal approximation will work.
But I think somehow the shock wave, as long as assume that the shock wave doesn't depend on x plus
For
and
this
x
part
minus
of it,
separately.
this part of it.
Yeah, so as long as the shock wave doesn't depend on x plus or and x minus separately, but only on one of them, that's already basically an iconal approximation. This means that the shock wave there's one component of momentum that's missing.
Yeah,
the shock wave.
maybe
Yes,
on
that's what I was saying. The exchange
maybe on
vertex
this
is
part
right.
of it,
Yeah,
okay.
the emission vertex is separate.
Yes, this is what
maybe for the nucleus, like
No. Thomas is saying it is right. The same thing. The exchange vertex, the one which used to be the left vertex, is iconal. The right one is focused.
well, I don't.
If it's a
No,
shock wave,
it's
then
not
it's
iconal. The answer is not iconal. I can guarantee you that. I know what the answer. Yeah, look. I mean, if you calculate the Coulomb field of a particle, okay, what this is sort of a dressed up Coulomb field.
See, his gluons have essentially the same rapidity as that line.
Yes.
And if they're the comparable rapidity, why don't you have non-iconal terms?
No.
So the emission,
So the emission of this
Emission
gluon is
non-iconal,
completely
of course.
non-iconal.
But the scattering.
But then the scattering,
No,
the scattering of the gluon is non-iconal. The scattering
Well, no,
of the
sure. No, surely this scattering is treated by just generating a phase. As you go
Right,
Okay, so
forward.
that's iconal.
Yeah, that part is iconal.
Okay,
But
so
then,
the emissions are
yeah, but then you have to use that field, which is the result of the iconalization of this scattering term, and then you have to analyze that produced field in the region where the field is. You
Yes.
can't make.
Your
can't
gluon
make
is
some
going in a
quantization.
forward
Yeah.
or fragmentation direction,
that's
and it's a difference in from what you
That's
do.
right. But that just says that what you're just saying there is that when I go across the sheet, there's discontinuity. Okay, and I don't have to study the details of what happens inside that sheet, and that's true. Okay. But then what I do is I get a field which depends upon, the phase which I get when I go through that sheet, and that field I have to calculate with all of the kinematic factors attached.
Right.
But you're right. It's not. That's the reason why it's a solvable problem. The nice thing about this problem is, it's a nice solvable problem which nobody else has solved, and that's the reason I don't think anybody else has solved it, unless Al has.
Well, it's a different problem. You're doing a classical calculation. I was doing very quantum calculation.
No, but I mean, returning to my very first question, if you pose it diagrammatically like this, and I understand you're interested in space-time distribution, that's a different question. But if the question is calculate the torque of the gluon production cross-section, I think people have done it in the hybrid formalism, and they just want the corrections to it. Indian should say something.
The frame that Al was mentioning.
What?
The frame where the projectile is faster.
Yeah, in the frame where the projectile is.
Where the gluon emission proceeds either before or after the scattering.
I'm sure that the momentum space distribution per se is much simpler than to calculate the combined coordinate space and momentum space distribution. But if you're going to use this for anything like, some kind of understanding of how the matter evolves, then you need both. And I don't think,
But so long the shockwave is transverse, it's invariant by in the transverse plane.
well, if it was inverse in the transverse plane, then everything would be equal zero.
No, he means,
It has profile.
no, but isn't your shockwave uniform in the transverse plane?
What do you mean, the shock wave, it has fields which depend on XT.
You have
Arbitrary XT dependence.
Okay.
Arbitrary XT dependence. We solve this for a fixed background field, which, and we can find a solution for any fixed background field with arbitrary XT dependence. Now, in the end, you want to average correlation functions of this, which involve line order phases.
Right.
But which ones you want to do, you need to know in the presence of that background field before you do the average.
But if the correlation to invariant by translation invariant in the transverse plane, then the resulting distribution of just moment, the linear function will be trivial. Because the transverse is invariant.
No, I mean, if you calculate this thing, for an average event, I don't even know that that's true. I mean, when you do a hydrodynamic simulation, okay, with some initial conditions of central region, I don't think it's a good approximation to treat the color glass fields as uniform as they would be on the average. You have to treat one for each value of the field, then do the simulation, then things evolve, and then in the end calculate the averages. So you do need the detailed XT distribution information.
Sure. Then you have to put that by hand.
And you get it from calculation. And then you also, in this case, you need to know the longitudinal distribution. And the longitudinal distribution is crucial here because you have the longitudinal distribution of the valence quartz evolving differently. The initial conditions for that, I think, are going to be different than what would be for the gluon. And there's some questions of understanding there, which, to be honest, I don't really understand how to think about that problem correctly. I just don't understand how to think about it. Every time I think about it, I think I understand it, and then the day later I realize I don't. So I don't know if you had that. Have you had similar feelings on this?
Well, we're doing something more simple, right? So,
Did what?
I mean, we do it more simply by just saying, decelerating.
Yeah.
Variance. There's a lot more put in by hand.
Okay, I'm done. Hey, boss.
Okay, any other questions to Larry? If not, I guess, let's move on to the next speaker.